Hi everyone, this is Kellen Dilladio. I'm going to be going over Lab 5. The purpose of this lab is to drop a magnet through a foil tube to demonstrate induced current in physical applications of Faraday's laws. So, the system is an aluminum tube and a magnet. I'm dropping it through the tube. The surroundings are the table and the earth. Some of the assumptions that we make are minimal air resistance so that the magnet falls straight downwards, that the magnetic and gravitational forces are the only acting forces. The initial conditions, the magnet is held at a height of 18 inches above the table. So some of the physical principles we're using are magnetic flux, Faraday's law, B sub r, and then Newton's second and third laws. You can see graphics of those on the right. So preview results is the experimental time average was 1.612 seconds, and the computational time was 1.79 seconds. So we can see here me dropping the magnet through the tube. And on the left, we can see the set of times that I got. It's pretty varied. And the time average is 1.612 seconds. And you can see some of the geometry for the tube there with the mass of 0.025 kilos. The dipole moment was 3.5, taken from Lab 3. So, checkpoint questions. Why can't we use a ferrous tube, for example, a steel pipe? The ferrous materials are not as conductive as copper aluminum and will not slow the descent as much. They also magnetize, meaning there could be some interference in the experiment. What happens to the magnets? How does this compare to the magnet falling in free space without a tube? There's an induced magnetic field from the aluminum tube resisting the fall of the magnet. If there was no tube, there'd be no resisting force, meaning the magnet would fall as normal. So here's the computational model. We can see that I define a B field using equation from lecture 43. And then also from lecture 43, we have the equation for the flux, the change in flux due to the falling magnet. And then we calculate the force on the magnet because of that flux. And you can continue calculating that in steps 7 and 8. And then find the velocity and position using time steps. On the right, you can see the graphics created by the code and the final time. So interpreting the simulation, it says the intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring, with red and blue coloring flowing in opposite directions, which is clockwise, which is counterclockwise. How do you know? So if you look at the flux through the tube, you would know that blue is clockwise and red is counterclockwise, right? Because the magnet is moving downwards and the force on top is going to be gravity and the force on bottom is going to be the magnetic force. And if you do right-hand's rule, you can find those clockwise or counterclockwise directions. What happens to the dynamics of the system when you flip the magnet around? Not much. I mean, you just flip the current and you flip the clockwise and counterclockwise directions. But other than that, not much happens. It still resists the fall. How does the total time in tube of your real-world system compare to that of the computational system? Right, it's 1.612 versus 1.79. There's a couple of things that could have gotten in the way of that similarity, which is timing. It was actually pretty difficult because I had to wait for the sound in order to stop the clock. So that was pretty difficult. And then also, it would sometimes slide against the edge of the tube while I was falling down, adding a frictional force. And then obviously there's like air drag forces that can get in the way. So yeah, there's some timing error in there. And then also the dimensions and finding an exact dipole moment could also be a little bit false. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So if we go back here and we look at this graph, you can see that the velocity kind of shifts around a little bit, meaning that the forces haven't completely balanced yet. Cool. What if the resistivity of the conductor will reduce as close as possible to 0? Right. So if the current in the tube would come closer to infinity, right? Because you can see in the equation down there, if you bring the resistivity down to 0, then the current goes to infinity, and then that would make the magnetic force just about equal to the gravitational force, preventing it from falling. And then if you cut holes into the tube, there would be less current flowing through it, reducing the magnetic force, so it would fall faster. All right, that's it. Thank you.